Hey guys, welcome to this new series. This one is interesting because we will go over how to actually pre-train a language model. So, um, a lot of tutorials, rather most of the tutorials that you see online are about how you start with a pre-trained language model and how you fine-tune it. You do see some theory of how pre-training is done, but never actual code. Um, if there is code, there won't be any data, or some tricks would be hidden from you because for pre-training, the devil is in the detail. And there are a lot of things that go into pre-training a language model. And luckily, the team behind OLMO, which is from Allen Institute for AI, U Washington, Yale, Carnegie Mellon, and NYU, have released the end-to-end pipeline in open source of how do you train a large language model from scratch. So this is pretty big, and they've not just released the tools or rather the code for training, they have released code for evaluation, they've released the model weights, they have also released the training data, which the last part is what a lot of people don't. So a lot of these trillion-dollar companies, they never release the training data, and I think training data is the training data or the training data mix um, is the key for training all these large language models. So in this series, my plan is to overview and also do a code walkthrough of all the code and of how these really large language models are trained. So let's get started. And yeah, so they have the weights. So a lot of times you hear, hey, Llama has open sourced their weights. What that means is they have only open sourced their architecture or only released the architecture and the weights, not how they got to it, not how the weights were trained. So here we have weights, we have code of how training was done, and also evaluation and how you can do your additional instruct tuning or any RLHF, and also the data set used for training. So this is pretty big, and we will go through all of this. So first of all, so in this video, I'd like to just give an overview of the paper, the architecture that they chose, and the high-level details. Okay, so let's get started. And so these guys say that they released a whole framework from data to training to evaluation tools, which is fantastic, and also the logs. And yeah, so what they did is they trained a 7 billion parameter model and a 1 billion parameter model. Now I know this is well, compared to the current free models, quote unquote, which are around 70 billion. This is a bit small, but I think this is still a start. And the teams here says that they have a 65 billion parameter model that is undergoing training as well as we speak. So that's all super good. And what they also say is that the training lasts for 2 trillion tokens, which I believe is a bit less than what the state-of-the-art models do, but you know what, we'll take it. So yeah, so let's look what this OLMO is. They basically have this is a decoder only model, which and the plan is to release 3 models. Right now they've only released 2, where you have a 1 billion parameter model, a 7B and a 65B, and they say the 65B is still training. At the time of writing, I don't know what's the current state. Maybe they released it, maybe they didn't. We'll take a look. The 7 billion parameter. So you might ask, why do teams typically have a smaller version? So with a smaller version, what teams typically do, these teams that train large language models, is they test that hypothesis about the architecture and how the training loss is converging on a smaller model. And those learnings are taken into account in the bigger ones. So the learnings from 7B now will go into the 65B. So that's typically how teams scale up. Okay, so the key architecture decisions that they made have been like, sorry, um, I accidentally clicked on a paper. The key architecture decisions are derived a lot from the Llama family of models and also a bit from Falcon, and we will see what are the key architectural choices. Now, there is no science behind these. There is some science, but not a lot of it behind these architectural choices. And people typically go with what gives them the best result with the data they have and the architecture, because the compute architecture a lot of time dictates the model architectural choices you make, because averaging things a certain way versus doing it the other way changes the results because of the precision arithmetics. So this is what these people found. So what they found was, so they reduced all the biases, or they removed all the biases for training and stability, to get training stability. The layer norms were non-parametric. I believe Llama used RMS norm, which has some parameters, while they used the non-parametric formulation of layer norm. They use Swiglu activation function, just like ReLU, and they use rotatory position embeddings, rope, and their vocabulary was BBE based on the GPT Neo, and some multiple of 128, closer to 50,000. Okay, so pretty standard choices. I don't think these, apart from a rope, the other choices make a lot of difference. It's just what they found got them a converging loss. So rope is the only big factor, but now pretty much every model uses rope, so even that is not surprising. Big thing, the data set. So in an earlier paper, this team from Allen AI had released this DOLMA, which is basically data for OLMO. I think so. That's the full form. And it's basically a corpus of 3 trillion tokens across n number of documents. So yeah, so this is how the stack is. The common crawl, which is typically used in pretty much all LLM trainings, it's the web page crawl. There are a lot of tokens, 2 trillion tokens, but then it's pretty noisy. That's why you need to add Reddit, which is somewhat noisy. Stack Exchange is higher quality, and Wikipedia and Wikibooks, which are much higher quality, but then you don't have as much tokens. So this is the mix that they used. Going back to this chart about the architecture, this is a comparison of all the 7 billion parameter models. So you see pretty much more or less all the same. Layer norms are slightly different. What's also different is the kind of attention people used. So OLMO used full attention, Llama used grouped query attention, and Falcon used multi-query attention. If you see one of my recent videos where I talk about Gemma, the good thing is Gemma team also did an ablation between grouped query attention and full attention, and also I think MQA multi-query attention, and they found like it was negligible difference. It's just GQA is more efficient. But I thought I'd just point that out. And also the Dolma pipeline has some filtering built in, so that, and deduplication. So you can be rest assured you can use it right off the box, because you can assume it's been at least quality checked to a certain extent. So basically you can also so this is just the pre-training. So all my models are just pre-trained on the next token prediction task. Now you can use these models to fine-tune them or rather instruct tune them, or do RLHF and all that jazz. So this is all, I believe they also have code for all of that. And then for evaluation, they have code, and they also have code for in-loop evaluation. So typically when you evaluate a model, you will start with the Hugging Face checkpoint, and then you'll run it through the hoops. The result is not, I mean, the inference that you'll get wouldn't be as efficient or as fast as doing in-loop evaluation. So what in-loop training evaluation is while your model is being trained, rather in between training, you will do this evaluation. The advantage is that during training, your model is already heavily parallelized. It might be split across like 10 machines with whatever, X number of machines with all the tensors spread out across. So that inference latency would be super low compared to when you have a single bulky model. Especially, we don't have a lot of good tools for inference parallelization at the moment. So I think that's where also the delta comes from. But yeah, in-loop evaluation is basically just running it online during training. Yeah, and then, now the training framework. This is the biggest thing. So as I record this video, the big frameworks that people typically use, now I'm talking about frameworks, like of course you can go and code up your own multi-GPU, multi-node parallelized code that a lot of teams used. So for example, what's that team from Twitter? What's the model from Twitter called Grok? I think the team behind Grok wrote their own framework in JAX, or it's a single JAX script, like 500 or 1,000 line long. Sorry about that. So you can do that, or you can use some standard frameworks for the parallelization. And the big ones are NeMo Megatron, which is by NVIDIA, which does the 3D parallelism tensor pipeline, and also what's the other one? Model or layer parallelism. Then you have FSDP, fully sharded data parallel, which is a native PyTorch thing, and DeepSpeed by Microsoft. Now, DeepSpeed and FSDP are kind of identical in how they work. Is they do this zero optimization strategy, and I urge you to check out what that is. But basically, what it is different blocks of models are sharded across different GPUs, and during training, the parameters or gradients are scattered or all gathered depending on whether it's forward or backward pass. And actually, let me pull up, give you a nice idea of like how it works. So DeepSpeed team had a nice image of, if I can, I can't find it. Let me pull up the DeepSpeed paper. Yep. So, right. So let's say you had n GPUs. Now, if you put n models across all the GPUs, you will need, let's say your model fits a GPU. If it fits or doesn't, that doesn't matter. But let's say for the sake of argument, it fits. So you split you have n instances of your model. But in DeepSpeed, what each GPU is responsible is only a part of the model. So this is responsible for the first part of the model, this is responsible for the fifth part of the model, this is responsible for the last part of the model. Now during forward pass, all the different GPUs will share weights with each other. So when the first layer is being evaluated, this GPU will send its weights to all other GPUs so they can do the forward pass for that bit and then release the weights. And then this GPU will transfer all the weights to all other, so it's sending its weights, and each GPU will do the forward pass and the weights will go away. So there's a lot of So this zero strategy is very memory efficient, but there's a lot of communication overhead. But you can check out the paper for the details. Maybe I'll make another video about it, but that's not the point of this paper, this current series. Yeah, so what they do is they use the FSDP framework, which we'll see the code, and they give details on like what their microbatch size was and so on for the 7 billion parameter model. So this is good. Like seeing how large language models are actually make use of these frameworks, or the teams that train these models make use of these frameworks, is pretty cool and gives us good insight. Then, I mean, they used mixed precision, which is pretty standard. RMW, again, standard stuff. How they group their data together in chunks of 2048. I personally don't like this group chunking, but that's the standard. They use the interesting thing is they trained on NVIDIA and AMD GPUs, and they saw similar performances. So, okay, that's good to know that the AMD hardware is also catching up. Yeah, this is a table of like all the parameters that they use for training, and so one thing to note is the gradient reduction, like across all the GPUs, the all reduce operation, and the optimizer states are both high precision FP32, while in some models like Falcon, their gradients are float 16. That's kind of interesting. Yeah, then there's some evaluation results, and the model performs. It's not state of the art, but it's doing decent. So it's doing decent for what they've done. I think it's trained on a bit less data, and that's the reason. But the good thing is they release all the details, and that's what we care about. So that is pretty much all I wanted to talk about in this video. But I would like to end the video by just checking out their code, or at least the web pages for their code. So let's go to the data. Oh, wow. I guess it's so big. The data set, this is the OLMO data set, and it is 4.5 terabytes. I don't think I'll be able to download this, nor do I think I would be able to show you the training. But I was oh, there's a nice statistics of the split. I was hoping to be able to view it, but yeah, this is understandable because it's so big. Let me see if they even have it on Hugging Face. They just have it, I guess, the URLs. Okay, that's perfectly fine. Let me see if the OLMO team has a web page. What did they have? I thought they had it. Just to see if they release a 65 billion one. Nope, doesn't look like it. No, yeah, you wanna hold on to your best model, I guess. Okay. This repo is the code. This is where we'll be spending most of our time, and it has all the training code and inference code. So inside this, there's a folder, OLMO, and this thing has all the code. The main things I'm interested in is the model file and the training. So the model file basically has pretty much how the model is defined, and also how it's being sharded. So remember, we talked about FSDP. So how FSDP is actually being implemented. So that's going to be cool. While the training is yeah, so they define their own trainer class. So that's also going to be interesting, is how they do the FSDP training. So that we'll go into details of what is being done, but honestly, it's not a lot complicated than having a simple model. So if you remember your Hello World LLMs, if you know that, the only additional here is this FSDP wrapping, and it's not too complicated. What my plan is to do is, if I can just load it in my local environment, like step by step evaluate the code or see how what is happening, what tensors are getting filled, their shapes and whatnot. We'll see. Like, it's not terribly important to do that, but that just makes it easier to explain. We'll see. But I guess this is all for this video. I'll see you guys in the next one.